Okay, good evening, everyone. Let me share my screen. This is Module 2. Today we are looking at electronic components. We are taking resistor as a case study. Previously, we noted that electronic components can be divided into two major categories: passive components and active components. Passive components can work without power. They don't need power supply for them to really come up, and they don't alter the signals. Something like resistor, inductor, capacitor. But active components will need to be powered for them to come up to really function. Something like an IC. If you connect all your ICs and you didn't power the IC, there is no way your system can work. Okay, so today we want to pick them one by one. We are starting with resistor. Okay, please confirm that everybody confirm that you can hear me.
I hear you, sir.
Okay, thank God today's network is friendly. So we move. We're going to look at basic functions of a resistor in electronic circuits. Pay attention. We are going to be doing some tutorials while the lecture goes on. At the end of each session, we'll look at the tutorial question. I expect somebody to answer questions. This is just a guide. I'm not the type that is restricted to what is on the slide. So you expect that I might just be myself as the lecture goes on, but we will follow what is here. But there are some other things that may not be here that can come up. We look at resistor color codes, and then we'll look at resistor key performance indicators. This tutorial will come at end of each section. Now, this is the symbol for the resistor. This is general symbol for resistor. We need to take note of that. We want to look at basic functions of resistor in electronic circuits. Basic functions. Number one, a resistor, by definition, limits the flow of current. So it's a current limiter. When we look at this circuit, this is 100 volt DC supply B1. This is 220 ohms. This is a variable resistor. This is an LED. This is an ammeter used to measure current, always connected in series with the load or to the load. When we say something is connected in series, what it means is that the same current will flow through the components. Things that are connected in series will have the same currents flowing through them. If they are connected in parallel, they will have the same voltage across them. So, this is a variable resistor connected as a potentiometer. So when we begin to, or what we call variac, when we begin to vary this resistor, later we are going to see that the current through this circuit will begin to vary. At the maximum resistor, we have the lowest current. At the minimum resistor, we have, that's when the percentage is 0, we have maximum current flowing through the circuit. This is one of the basic functions of a resistor in a circuit. Anywhere you see resistor in a circuit, just know that one of the things it does is to limit the flow of current. And then the law that controls that is Ohm's law, which tells us that the voltage developed or the current flowing through a resistor, the voltage developed across a resistor is directly proportional to the current flowing through it. Either way, this is the equation. V is equal to IR. So the voltage is directly proportional to the current. By the time you introduce the constant of proportionality, which is the resistance of the resistor, you get that equation. Meaning that if you increase the voltage across a resistor, the current will increase. If you increase the resistance, the current will reduce. So at any point in time, when you multiply the value of current flowing through a resistor and the value of the resistor, you get the voltage across that resistor. We move on. Another major function or importance of a resistor in a circuit is that we can use it to form a voltage divider. You can actually divide the voltage across a circuit within a loop. Look at this circuit. This is still the 100-volt battery, DC battery. So this is the circuit. This is the circuit. Just watch my mouse. This is the circuit. This is the positive of the circuit. It flows from here back to the negative. So this is 10 kilo ohms, 10 kilo ohms. When we simulate this circuit, we are going to notice that this voltmeter measuring the voltage across R2 and the voltmeter measuring the voltage across R3 will be reading the same thing because they have the same value of resistor. This is the variable resistor. So as we vary this, the voltmeter across this variable resistor will be changing as well as these ones. But at any point in time, this V and this V, that is V2 and V3, will be the same. There is a law, another law this obeys. We call it Kirchhoff's voltage law. We say that algebraic voltage about a loop is 0. This is a loop. This is a circuit. What it means that this is 100. When we sum the voltage across 10K and this 10K and this variable resistor, they will always give us 100. So algebraic voltage about a loop is always, there is sum of the algebraic voltage about a loop is always 0, meaning that 100 minus this minus this minus this must give us 0. That's voltage divider. And at any point in time, as we progress, you progress in your practice of electronics, you will notice that this is a very important concept. Another key function of a resistor in electronic circuits is what we call voltage referencing. referencing. We will not be able to cover everything about electronics within 1 month, but we will try. There's what we call voltage referencing, especially when it comes to operational amplifiers circuit. Your operational amplifier basically has inverting, that's negative input, and non-inverting, positive input. When we want to configure it as comparator, we normally make one of the pins, that is one either this or this, either inverting or non-inverting. The voltage must be constant. One of the ways to make the pin constant is to reference that pin using a voltage divider. Just use one fixed resistor. You can see that this is a fixed resistor, 10K is not varying. And then another variable resistor, you set it such that it doesn't fluctuate. Because if this one is fluctuating and this one is fluctuating, you are not going to get desired results. What this circuit is doing, even though I don't expect us to understand that in detail from at least at this level. This is a circuit you can use to detect presence of light and absence of light. This is circuit that can be employed on automatic street light control because this is a light-dependent resistor. So what happens is that during the day, the resistance of this decreases. And when the resistance of this LDR decreases, the voltage on this pin 3 will decrease. And when it decreases, this op amp will switch off. The op amp will switch off. But in the night, the resistance of this LDR will increase. When it increases, the value of voltage on pin 3 becomes greater than the value of voltage on pin 2. And then the light comes on. Or we are using just this small LED to represent the street lights. At this level, when we progress, this can actually be interfaced to other components to drive a heavy load. So this voltmeter here measures this output voltage. This voltmeter measures the reference voltage. This voltmeter measures the voltage across the LDR. Remember, we're not dealing with LDR, we're not dealing with an operational amplifier, we're not dealing with street light. It is this section we are dealing with. But then we can't treat it in isolation. I feel we should see it the way it is being used in a circuit. So the voltage here will be constant. It shouldn't be changing. Now let's simulate it. Let's see the simulation. Oh. I want to simulate it using Pro Tools Design Suite so that we drive home the points. Can you see my Pro Tools Design Suite? Please confirm you can see my Pro Tools Design Suite, the new window I just opened.
I can see it.
Okay. Now, this is the first application. That is the first basic function of a resistor current emitter. Let's run the circuit. You are going to tell me what to observe. That is the only way I can confirm that you are listening. and your mind is in the lecture, okay? So I will just operate this. Tell me your, probably I should increase this. Tell me your observation. So somebody should tell us his or her observation why I change the variable resistor value.
Good evening, sir.
Good evening.
When you increase the resistor, the currents reduce. That is the ammeter, the reading reduce. But when you reduce the resistor, the ammeter, the reading, the ammeter, that's the current increases. That's what I
Okay.
observed.
Okay. So please, your name?
My name is Ben.
You say?
Ben. Okereke Ben Chigozie.
Okay, Ben. So we can confidently
Sir.
confirm that resistor limits current flow in a circuit. And if we increase the value of the resistor, say we increase it to 100K, the value of current will still reduce more. You can see, what do you observe now?
No current flowing.
No
There's no
current is
current.
no current is flowing because I've practically increased the value of the resistance. This is the only time it flows, but at this time, even the LED is no longer on, simply because I increased the value of this resistor. If I should, if I should reduce it, so say to 0.1, that should be about 100 ohms. You see, the value of current has done what? What happened to the value of the
Has
current?
increased.
It has increased.
It has increased. Yes.
Okay, so we move to the second point, which is voltage divider. Oh, I need to centralize this. Okay. Now, I want you to tell us, another person, tell us what you observe about the reading. This reading, this reading, this reading. Not Ben now, another student in the class. Let's put it this way. Somebody should use your calculator and sum the voltage across R2, R3, and this variable. Tell us the value. Is Chukwud in the meeting? Chukwud is not
Hello,
there.
boss. I'm in the meeting, I'm in the meeting, but I'm driving. That's not the problem.
Eh?
I'm driving.
Who else is in the meeting? Who? Frano, are you there? He said they just logged in and they're busy with something else. Okay, Ben, since you are the only one active, sum this and this and this. Let's get the value.
Hello, sir.
Yeah, sum the voltage across R2,
100 volts.
100 volts.
100
Okay,
volts. Yes, sir.
so it's confirming Kirchhoff's voltage law. Now, I want you to compute 10 over, okay, we don't know the exact value of this, so you may not know exactly what it is. But let's watch this. At any point in time, the voltage across R2 and R3 are the same because they have the same value. But they are changing because this one is changing. Now, calculate again the three voltages. Let's know what it came up to, or they came up to.
So it's still 100 volts.
It's still 100 volts. That's why I said
Yes, sir.
that Kirchhoff's voltage law says that algebraic sum of voltage about a loop is equal to 0. In other words, the source voltage must be equal to all the voltage drop across the elements when they are summed together. This is a very important concept in electronics engineering, not just in electronics engineering, in engineering, both electrical and electronics. We move over to the third function of a resistor, which is referencing voltage. And so we can see here that this voltage is referenced to be 2.63. I can change it. We can actually change it, but then once we change it, it remains where it is. So the basic operation of op amp is that once port is connected to non-inverting, that's positive pin, is bigger than what is connected to negative pin. The output will be equal to 1, or what we call high. Pin 8 for this LM358 is the power pin. Remember, we talk about active components. LM358 is an IC, is an active component. So it needs power to actually operate in a circuit. I want us to be seeing this thing. This is an active component. You can't connect it without connecting the power supply. But when it comes to resistor, you notice you just power the circuit and everything is working. For active components, after connecting the circuit, you have to power the component itself. Otherwise, it's not going to respond. Now, so this is fees at 2.63. That is voltage at this point. Let's try to change the voltage here, which is voltage at pin 3 is 3.28. Let's try to reduce it. Once it goes below 2.63, this LED should go off. Do you see that?
Yes, yes.
Okay. So basically, that is where operational amplifier works when it is connected as a comparator. But we're not dealing with operational amplifier today. We have said that resistor can function in how many ways? If you can answer this simple question, it means you are not listening
Three ways.
It means you are not listening attentively, and
I answered
I wouldn't
three
actually
ways.
like it. I will look at it as I'm wasting my time.
I answered. So I said three ways. In three ways.
Okay, mention them.
Voltage referencing, voltage divider, and opposition of flow of currents.
Good. Great. So we can proceed now. So this is a tutorial. When we say that, let me see if I can get a whiteboard. Let me share the whiteboard. Just a minute, it's trying to load the whiteboard.
Okay, so
Okay. When we say that things are connected, components are connected in series, um, this whiteboard, when resistors are connected in series, we mean that the same current flows through them. So this is R1, R2. You can see the whiteboard. Can you see the whiteboard?
Yes, sir.
Okay. So a current flows in this circuit. This is positive of the circuit, this is negative. Then current I flows through the circuit. We say they are in series because the same current flows through R1, R2, R3. So the effective resistance that this circuit sees is equal to R effective, which is equal to R1 plus R2 plus R3. And then when we want to find the current, if this is V, we simply do I is equal to V over R effective. So if this is 10 volts and R1 plus R2 and R3 summed up to be 10 ohms, then the current flowing through the circuit will be 1 amp. If we now want to find the individual current voltage developed across this, we multiply each resistor with the total current. What I just explained, is it clear to you?
Yes, sir. Yes, sir. It's clear.
Okay. Let's clear this one. I would like you to confirm, you can verify that by the time you check all the voltage, get all the voltage across individual resistors, you will narrow down, you will come to this equation that V1, that is voltage developed across R1, is actually equal to R1 all over R1 plus R2 plus R3, all of them multiplied by V. You can verify that later. And if that is the case, what do you think will be the value of V2? If you want
That
to,
should be R2 all over. V2 should be R2 all over R1. Should be R2 all over R1, R2, and R3 multiplied by V.
okay. So the same thing applies to V3. Later, we'll talk about resistor being connected in series, in parallel, but it's not a big deal. When resistors are connected in parallel, when they are connected in parallel, it simply means that the same voltage will be developed across them. the same voltage but different current. The same voltage will be developed across them. They are connected across the same voltage. So this is plus, this is minus. So the same voltage, but then the resistance are different. So different current will flow here, different current will flow here, different current will flow here. The current coming here will divide into 3. The highest resistance will get the lowest current. These are not the things somebody should cram. It's as simple as that. If the resistance opposes the flow of current, it simply means that the higher resistance will allow smaller current to flow. So if we have R1, if we have R1, R1, R2 here, and R3 here. If R1 is the smallest resistance, has the smallest resistance value, then the highest current will flow here. Later, we will look at the mathematical models that control this. But I think for now, we are okay. So that's that. We go back to the lecture proper. So let's look at this. Figure 4 shows that these resistors connected across a 100-volt DC supply. Calculate the total resistance of the circuit. What is the answer? What is the answer, please?
$17,000 ohms.
You say?
17,000 ohms. 17K ohms.
17K ohms. Okay. So you can use this formula to calculate the voltage across each one. Let's proceed. We come to section 2 of this class, which is resistor color code. If you see a resistor, they come in different colors with different colors. Each of them has a significance. Let's start with, okay, your basic colors you will see include black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and sometimes you have none that looks like white. You will recently, you begin to see that resistors come in different, not just with 4 bands. We now have 5-band resistor, 6-band resistor, but the pattern of reading is the same. Let's start with this one. You need to follow me carefully. Let's start with a 3-band resistor. The first 2 colors are always the digits. The digits. Then the 3rd color is what we call the multiplier. What it means is that, for example, this resistor now, this color is this particular color I'm pointing is orange. So that's 3. orange, another 3. Then, which color is this? Which color is this?
Looks red.
Is that red?
I think so.
Okay, let me increase my distance. I don't think it's red, it's brown. It should be brown. This is red. It's brown. And brown here is the multiplier for brown is 1. So, and there is equivalent, that is 10 raised to power 1, which is 10. That's why the value of this resistor is 330 ohms. And then the multiplier, what do you call it? The tolerance. The tolerance is none. That's why it's 20%. I take this one again. This color is gray. Look at it. Gray. This one is red. So we have 8-2. 8-2. Then this one is multiplier, and the code that match that thing here should be, looks like yellow. No, not yellow. Orange. Orange. So we have 82 multiplied by 1000. That's why it's 82K kilo ohms. And then gold. Gold is tolerance. And gold for tolerance is how many percent? 5%. Tolerance means 5%. Somebody compute 5% of 82,000. 5% of 82,000. That is 5 over 100 times 82,000 over 1. What did he give us? Or what does it come to?
That's 2005,
Eh?
2050.
1,000.
I'll be that. 2050. Are you sure?
2,000. We're talking about 5%. That is, let me be sure. 82,000 divided by 100 times 5. I hope I'm correct. 4,100. 4,100. So what it means is that if you use your multimeter to check this resistor, it will be 82,000 plus or minus 4,100. That is the range. So the range you are going to get will be 82,000 plus or minus 4,100. So it could be 80, the maximum limit will be 8,600, or that is 82,000 minus 4,100. That is 82,000 minus 4,100. So you can get 77,900 or 8,600. The range will fall within there. Definitely, this is not a good one. It's good, but for precision circuits, it's not nice. If we have 4 or 5 color bands, then the first three becomes the digits. The last one, the fourth one becomes the multiplier, and the other one becomes the tolerance. So somebody should tell us the value of this resistor. Tell us how it is gotten. Let me be sure you are following. This is 5 bands. Have you seen a 5-band resistor before? Ben, have you seen a 5-band resistor before?
No, sir.
Okay, Prof will show you that when you
No,
get
sir.
to the lab. That's that.
Okay.
This one, you
The
see,
distance is 521.
yes, it's 521, but because this is green, which is 5, this is red, which is 2, and this is brown, which is 1, so 521. And then for black, multiplication factor of black is 1, so it still remains 521. Then for tolerance, you follow here. Tolerance for brown, am I correct? Is this brown? Tolerance for brown is 1%. That's it. You follow the same way to calculate this. So that's a way to calculate the resistance value in case you don't have your multimeter. But then multimeter will not give you the tolerance. Multimeter will not give you the tolerance. But multimeter can give you an approximate value. You have a rough idea of what the value of the resistor is. I've already explained this. Resistor color code use color bands to identify resistance, multiplier, and the tolerance. This is IEC 662 standard. I think we have explained this, so let's move. Another way to measure resistance value is by the use of multimeter. Multimeter. This is number 2, not number 1 now. We have done number 1. By the use of multimeter. When you pick your multimeter, there's always a resistor range. Even if it is multimeter that is auto, you just look at that meter properly. So this is resistor range. You will, if you don't have a rough idea of the resistor you are having, well, you can start with smaller range. If you put it at 200, if it's not reading anything, if it's reading 1, then know that the resistance is above 200. Then you put it on 2000. Some meters will write 2K, 200K. You just need to note the range where you have placed your knob. Just turn this knob to this point. And then you touch the terminals of the resistor and check what comes up. You don't need to use your hand and hold it. If you use your hand, 2 hands and hold it, it's going to affect the value for a reason we're going to discuss later. Temperature affects the value of resistance. So the value you get while holding the resistor with your hand and the value you get while the resistor is on the table will not be the same. Definitely not going to be the same. Then you need to take note of the range where you are. If you measure, for example, you have a resistor, your meter is in the range of 200K, and you measure two terminals of the resistor, you are getting 2.14. The real value of that resistor will be 2.14K because you're in the range of K. So it's 2.14K, which is actually 2,140 ohms, approximate value, because multimeter will not give you the exact value of the resistor, but it will give you a value that is within the tolerance range. And that is that. So when you get this light, you attempt this tutorial. That is what will help you to internalize the lecture. The value of the resistor shown in figure 7 is dash. The value of the resistor shown in figure 8 is dash. A multimeter in 200K resistor range was used to measure the value of a resistor. The reading on the meter showed 2.14. What is the approximate value of the resistor? I think I've answered the question. So you can explore such questions around, more questions around this line. Excuse me. Let's proceed. Now, key performance indicators, KPI. KPI. This is very important for designers. KPI for resistors. Do we have any questions so far?
No, sir.
Okay. Number one KPI for resistors is what is called temperature coefficient resistance, TCR. The temperature coefficient of resistance, or TCR, is one of the most important parameters that characterize the resistor performance. The TCR defines the change in resistance as a function of the ambient temperature, that is room temperature. The common way to express the TCR is in either parts per million per degree centigrade or parts per million per Kelvin, that's degree Kelvin, which stands for parts per million per degree Celsius or Kelvin. Okay, I've said that. The temperature coefficient of resistance is calculated as follows. The formula is there. What that simply means, if you know the resistance value at room temperature, that is when the resistance value is given, just know that it is resistance value at room temperature. As the temperature increases, depending whether the resistor has positive TCR or negative TCR. If it has negative TCR, as the temperature is increasing, the resistance will be reducing. If it has positive TCR, as the temperature is increasing, the resistance will be increasing. So, this is one of the reasons why control system designed, say, in US, for US environment may not work in Nigeria. You bring it here, you think that there's a problem with the system. There's no problem with the system. Our temperature and their temperature is not the same. If it is designed to work in that environment alone, once it comes to this environment, especially in the north, if it is a car, the automation system of that car might begin to have issues. And then somebody who doesn't have this understanding might think that the car has a fault. No, it doesn't have any fault. It's just that the temperature has shifted and then the resistance has also shifted. So many things about the control system, especially the set point, will shift. Okay? That's that. At times, TCR is presented with alpha. We proceed. Resistance value for conductors at any temperature other than the standard temperature, usually specified at 20 degrees centigrade, on the specific resistance table must be determined through this formula. That formula is a direct result of the other formula. R, that is mu R is equal to RF into bracket 1 plus alpha into T minus T ref. I think this is a simple, very basic formula that is not difficult to grab. R is conductor resistance at temperature T. RF conductor resistance at different temperature. Alpha temperature coefficient of resistance for conductor material. T conductor temperature in degree Celsius. And T-ref reference temperature that alpha is specified at for the conductor material. So each material has different conductor, different TCR. You can see the table displayed. We are having some components. There are silicon, germanium, carbon, up to lithium. So let me ask this question. The resistance, internal resistance of a diode, will it increase or decrease with increase in temperature? The internal resistance of a diode, will it increase or decrease with increase in temperature based on these data available to us now? Nobody is talking.
I don't even know which one is diode. I'm not seeing any diode here.
Diode. I just asked an applied question. We've discussed diode. Diode is a semiconductor. Diode is a semiconductor that is manufactured using either silicon. The base material is either silicon or germanium. Did you hear that one?
Yes.
Good.
Okay.
So
If
based
it's
on that now,
this thing,
increase in temperature, will it make the resistance of diode to go up or go down?
I think it will make it go up.
Why?
The TCR is negative. You say the TCR is negative, it will make it go up. The decrease will make decrease in temperature. And the decrease in temperature will make decrease in this thing, resistance. So increase in temperature too should make increase in
Okay.
resistance.
If that is what you heard, if that is what I said, then it's a slip of tongue. I said, when TCR is negative, it means that the increase in temperature will lead to resistance of that material. If TCR is positive, it means that increase in temperature will lead to increase in resistance. Look at the graph. Can you see this graph?
Yes.
So this is a positive TCR, and it has a positive slope, meaning that increase in temperature will lead to increase in resistance. This one is negative ppm, showing us it has a negative slope, showing us that increase in temperature naturally will lead to increase in temperature will lead to decrease in resistance. And then we can see copper. That's why conductors.
Excuse me, sir. Excuse me, sir.
Go ahead.
I'm still, like you said, increasing or something that have negative TCR. Increase in temperature will lead to decrease, right?
Yes, increase in temperature. If it is negative, if TCR is
Yes.
negative, increase in temperature will lead to decrease in resistance of that material.
Okay. They are inversely proportional. One is negative.
Well, put it any way you understand it. What
Okay.
is clear in my thoughts, in my mind, is that if something has negative TCR, that is temperature coefficient resistance is negative. What it means is that as the
Okay.
temperature begins to increase, the resistance begins to decrease. You can put it anyhow you want to
Okay.
understand it, or anyhow you understand it. Once you hear
Okay,
that
sir.
a
Okay.
material has TCR that is negative, just know that once the temperature begins to increase, the resistance of that material begins to decrease. Is that clear to you? Is that clear to you?
Yes, sir. It's clear to me.
Okay. So something like copper, we can see why when the temperature increases, the resistance will increase and the losses will increase because loss is connected to I square R. Loss is connected to I square R. I square R. Power is equal to IV. V is equal to IR. So when you combine this now, when you substitute V here, you get I square R. So the loss is connected to I square R. We call it I square R loss. And is dissipated in form of heat on the resistor. Okay? So any material with positive coefficient TCR, once temperature begins to increase, it begins to heat up because the resistance will begin to increase and this component will begin to increase. Okay, so we go back to our screen. You can, this is a practical thing now. Look at this circuit. At this temperature, this is value of this, this is value of this, this is value of this. And then, if you use the formula we use to compute the voltage across each element, the total voltage there is 14. The voltage across this load, you will get it at 12.5. Then this wire and this wire are the same thing. You will get 0.75 volts. So the current flowing through this, which is V over the total resistance, will be 15 milliamp, 15 milliamp, 15 milliamp, 15 milliamp, because they are connected in series. So, and okay, these are the resistors. This is total resistance. But when temperature increases to 35, you now use that formula to see. You will see that you will see when you compute this, trying to get this. When the temperature increases to 35, you use this formula to compute that R, this 15 ohm resistor will have increased to 15.905. It may not make sense for us here, but in real-time systems, it's a very big stuff. So if you use that value and recompute, you notice that the voltage across the load, which is R, would have, where is it? The voltage, this is the total voltage, is still the same, but the resistance has increased. So the resistance of the load has increased to this point. What happens is that current across the load will reduce. I hope I'm correct. It will reduce. Similarly, there is the same current across the entire load now, the entire system now. But key point here is that you notice that the voltage across your load will decrease. The voltage across your load will decrease, while the voltage across the resistors will increase because their resistance value has increased, and this can bring instability to the entire system. It's a very big concern. As you can see, voltage across the load went down from 12.5 to 12.42 volts, and voltage drop across the wires went up from 0.75 volts to 0.79 volts as a result of temperature increasing. Though the changes may seem small, they can be significant for power lines stretching miles between power plants and substations and loads. In fact, power utility companies often have to take line resistance changes resulting from seasonal temperature variation into account when calculating allowable system loads. So these are the KPIs we need to take note of. I've already talked about resistance tolerance. We have to take note of that. For precision circuits, resistors that have small tolerance should be chosen. Finally, the resistor wattage, that is in the KPI, the resistor wattage. Resistor comes in various sizes. You have quarter watt, you have half watt, you have 1 watt, 2 watt, 5 watt, you have 10 watts. Apart from the resistor value, we also need to consider the amount of current flowing through the particular point we want to connect the resistor, we need to make sure that the resistor should be able to dispatch, be able to handle the heat that will be generated. That is heat as a result of I square R loss. If you take a quarter half resistor and connect across 220 ohms, there is every likelihood that it will burn off. Can it pass the current? Yes. Can it withstand the heat? No. That's that. So, this is the final tutorial. An electronics instructor wants to demonstrate to his student the effect of electrical resistance changing with temperature. To do this, he selects a carbon resistor about 3 centimeters in length and 5 millimeters in diameter, black in color, with a wire at each end, and connects it to an ohmmeter. Whenever he grabs the resistor between his fingers, the ohmmeter instantly responds by showing a greatly reduced resistance. The question is there anything wrong with this experiment? Who can answer?
His hands, his hands, the temperature decreasing the distance
You say?
is part of what is reducing his temperature. The temperature from his body is reducing the resistance.
Okay, that's correct. Number 2, if we were to plug an electric source into a very long extension cord and then plug the other end of the cord into a power receptacle, we will notice a decreased level of performance from the saw as compared with how it performs when directly plugged into the same receptacle with no extension cord. Determine if the source performance becomes better or worse at the ambient temperature as the ambient temperature increases, and explain your answer. Of course, based on what we discussed, you can try this out. Most times you notice that you plug, and then even if it is the same diameter of wire, as the temperature begins to increase, the performance of your system begins to drop. And these are the calculations you can do on your own using the formula. Calculate the resistance of each of these specimens, given their resistance at the reference temperature and their present temperature values. One of the ways to internalize the lecture is to lay your hands on tutorial and practice it so that the thing will become part of you. Thank you so much for listening. We have come to the end of today's lecture. If you have any question, you can go ahead and ask. Any question? Okay, no question.